Welcome to the Richard Lloyd USA YouTube channel. I'm Richard Lloyd. Today I'm going to show you how to make a custom power supply for a Raspberry Pi. In my case, it's a Raspberry Pi 4B. This should cost you under $7. Is what I made it, and it is a great power supply. It's the only power supply system that I use for my 5 Raspberry Pis, and it works amazingly well. In fact, I have had one running as a server now for over a year with the same power supply that I'm going to show you how to build in this video. So let's get at it. All right, I'm sure somebody noticed that this was a Raspberry Pi 3. Again, this power supply we're building will power up any Raspberry Pi. You would just have to change the USB-C cable for a micro USB power port for the Raspberry Pi 3. But I wanted to show you these cases, number one, because I no longer use a active cooling fan case anymore, because I had to replace the fan twice as it wore out on me, and I found it to be noisy as well. And again, I have to worry about the fan failing. On these passive cooling cases, there's no moving parts. They cooled them down just fine. Never had a problem with overheating with any of these heat sinks that are basically screwed onto the Raspberry Pi, and they look really sharp. They're quite handy. These work great. These kind of screw-on cases, and again, I'll put links for this stuff in the video description below. But for me, this is my favorite because it protects the Raspberry Pi all the way around. Sort of seals it, and it keeps it nice and cool, just as cool as these do as well. But it is slightly larger, as you can see, in width. And also in all the way around, just bigger, right? So yeah, but whatever you wish to use, you can use, and I'll put the links for them in the video description below. Let's get on with building a power supply to power these things up. Here's all the components you're going to need to build this power supply, custom power supply. The heart of the whole thing is going to be this little circuit board here. That is an XL6019 boost buck converter, and these are available on Amazon or eBay, and again, put links for that in the video description below. I'm using a power supply here, which is a laptop power supply. I got it at a local thrift store for $2.99, and that was a great deal. But you can get these just about anywhere, and if I find some on Amazon and eBay, again, I'll put the links in the video description. This one's the reason I like the laptop power supplies is because they're universal. They can work anywhere. This will take 100 to 240 volts at 50 hertz to 60 hertz, 1.5 amps. That's the input, and the output is 18.5 volts at 3.5 amps, which is a total of 64.75 watts, or 65 watts if you really want to be, just round up to 65 watts. And in order to power a Raspberry Pi 4, they recommend, actually the power supplies that they sell for Raspberry Pi 4 are usually about 20 watts. So this power supply actually has enough wattage to power 3 of them. And you could do that. You could hook up 3 of these boost buck boards to this power supply here and run 3 separate Raspberry Pis. Another nice thing about these modules is that you don't need one of these for every Raspberry Pi. You could get a big enough power supply at 60 watts. I got a 90 watt one, and every 20 watts is another Raspberry Pi. So, and if you want to find out how to figure out how many watts a power supply is, it's just multiply the output, which is the voltage, and by the amperage. In this case, it would be 18.5 by 3.5 amps. 18.5 volts by 3.5 amps, which is, again, 64.75 or 65 watts. So enough to power 3 Raspberry Pis. And just so you know, I've done a lot of testing on these boards, and I've never seen a Raspberry Pi be able to draw 20 watts yet. I've tried everything, connecting hard drives to it and everything else, and again, towards the end of the video, I'll do some testing on this. But right now, this is what you need: a USB-C to regular USB cord. Length doesn't matter really, and that's it. These are the components you need to make this. Next, I'll show you the tools. All right, here's the tools and supplies I'm going to be using. You can improvise as you wish. I've got soldering wire. This is 60/40 thin soldering wire with rosin in it. A soldering iron, and again, links for all this stuff in the video description. A very cheap meter. You don't need anything expensive or crazy. This is like $7 just about anywhere. I think I bought this at, Harbor Freight. And again, I'm going to be using a better meter, but I'm just saying a real cheap, easy meter that can measure voltage accurately will be good. Wire cutters, a jeweler's screwdriver. This is a flathead. You're going to need that to adjust the little adjuster for voltage on the circuit itself, and a set of wire strippers here. But again, you don't need wire strippers. You can do that with a suitably sharp knife if you're careful. And nice to have would be a set of alligator clip cables like these, just to jumper things together so that it's easier to test your voltages and so on. But you don't need them. It's just optional, nice to have, tools. So that's it. So this is all you need. Again, all the links in the video description below. Please use those to help me out. And next, we're just going to put it together. I'll show you how to do it. Not sure whether I mentioned it or not, but the power supply needs to be a DC output power supply. Some of these are AC output. I don't think for laptops they are, but a lot of, just check the power supply and make sure that the output says DC and that you've got a total of at least 20 watts. Also, I would say, go for something above 5 volts, like 8.5 on. I used a Sony PlayStation power supply on one of these supplies, and it's 8.5 volts. So yeah, it's something like that. 5 volts will do, but it had to be 3 amps, and I think 5 volts at 3 amps are pretty hard power supplies to find. So again, whatever you choose, just make sure it's 20 watts. What we're going to do here is cut the end off the supply line. This is the supply side, and you know what? These little connectors may come handy for you, or at least for me in the future. So I'm going to cut it off a little further back. We've got lots of wire here because of the laptop power supply is so long. So, and we can always extend this if we wish to. So I'm going to cut it, around here, and that'll give me lots of extra wire to use this connector again. Kind of my way of recycling. There we go. Well, it goes flying off. So next we're going to strip this back, and then get at the 2 wires that feed power to the laptop. So I'll do that next. Okay, safety first always. What I'm using, a really sharp knife here, and I'm just going to cut lightly around this insulation so I can get at the wire. And I just spin the cable, and like I said, very carefully. And usually it splits quite easily, like you just saw there. It just splits. There we go. Twist it off, or just pull it off, and ta-da! We've got 3 conductors here, but actually only need 2, which will be the positive and the negative. Again, this is why we need the wire to test for voltage. Okay, here we have the wire. To be honest, the 3rd wire is a bit of a surprise to me on this one, but we'll use the meter to test out which ones give us the proper voltage. We'll go from there. So let's strip them back. And you see why the wire strippers are so nice. All right, very clean at doing that job. Pull off the insulation. There we go. Like so. Then I'm going to power up this brick, and we're going to test out these leads, see which ones give us the 18 volts and which one's positive and which one's negative. Well, don't go by the colors, because it's not always, intuitive. All right, so I've got it powered, the brick powered up, and I've connected my leads, and you can see here that the positive is the green wire going to the white lead from the power pack, and the negative is the white jumper going to the black cable. So positive is the white, negative is the black cable, and the blue cable, I'm not sure what it is. It's not really giving out any voltage. I'm thinking it is a test wire, or a voltage check wire, or maybe an on and off. I'm not sure, but I could figure it out, and it doesn't really matter, because what we need is the 18 volts DC, which is what we got here. well, whatever you get on yours, it doesn't matter as long as it's 20 watts. And the way you know whether it's which one's positive, which one's negative, is that if you reverse this, and this is why you need a meter, all right? It's obviously why you need a meter. Always got to verify the polarity, because if you plug the voltage in backwards to this board, you will blow the board. And I have many examples of that, and I'll show you that. Actually, this one's one of them. It's got a chip right off it. It blew right off. So yeah, don't reverse polarity. Polarity is so crucial in this, and that's why you need a meter. Now you see here the negative. That means I've got the leads on backwards. In other words, the negative lead is on the positive, and the positive lead is on the negative. So by reversing that, doing this, now you can tell, because that negative symbol goes away, that that's correctly hooked up. So we've got positive and negative correctly connected. We get 18 volts, and I'm going to cut that blue lead back to the insulation so that it doesn't short with either one of these or anything else, right? So we'll keep it nice and clean and continue on from there. And then I'm going to tin the ends of these wires so that there's solder on them, so they go onto the board really nice and easy. I want to show you this neat thing on my soldering iron. It's got a temperature selection and a screen telling you the temperature as well. Currently got it set for 428 Fahrenheit, but it's variable from 356 Fahrenheit to 896, or 180 Celsius to 480 Celsius, and you can switch it from Fahrenheit to Celsius. All you got to do is hold both buttons down, unplug it, hold both buttons down, plug it in, and it'll give you the option to change it from Celsius to Fahrenheit. So right now 428, but I found this to be really handy. It's a great soldering iron. Again, link in the video description below, because some circuits can't take a lot of heat, and sometimes you need a lot of heat, because, like, for instance, you're trying to solder a really thick gauge of wire or something, and you want more heat, and you can choose it. You can dial it up and dial it down. So you can start from very low and work your way up to something that works for you, or from very high down to something that's not going to burn something. Okay, so really cool in that way. Let's solder up these two wires and tin them. The reason you want to tin them like that is because it makes it much easier to get them to adhere to the board afterwards. When there's solder permeated through them, they just make better contact. And they're also about 3 times longer than they need to be, so I'm going to cut them back so that the insulation is snug next to the board, so that there's not so much area of the wire available to short, right? So the less of the wire that shows from the board or extends out from the board that's bare, the better. So I'm going to cut these back, but I always make them long like this because basically it's easier to tin them that way. So you want to do the tinning process because it basically makes a really stiff wire that doesn't fray on you when you're trying to contact to the board, and it basically just works better. All right, here's the board straight out of the packaging bag. It comes like this, at least mine did. Open it up, pull it out, and I'll show you something about it. That's okay. So when it comes, you see the board just like this. You probably notice that mine don't quite look exactly like that. I don't know where I put my bare one at, but basically here's my test board, and you can see that it's a little shorter. This little tab here is for manufacturing, right here, this little red part. So I just snapped that off, so I'm going to do that now. Just snap it off. It doesn't do anything to it. And now you've got access to the points where you're going to put the wires and connector on, as you can see. Also, you can see this little tiny adjustment screw here. That's why you need that watchmaker's flathead screwdriver. So again, just snap that off. And next we're going to prepare the pads for the wires. All right, I like to put a little dome of lead over each one of the contact points, so I'm going to do that here. Reason for that is, hey, just makes the wire easier to connect. You know, here we go. Let's put a little bit more on there. Okay. And number one rule of soldering is the smoke will go up your nose no matter where you go. So be careful with the smoke. Get in a well-ventilated area, which I am. So you see there, two little domes, nice and shiny. Do it on the other side too. That's it. So those pads are now ready for contact with the wire, or soldering with the wire, and they are labeled as in and out, negative and positive on both sides. So that's really nice. Printing small, so but it's there, so you can make sure that you get polarity right. Again, what I said about polarity, you get this wrong, and this is what will happen to you. I'll show you my. I've tested these boards out extremely. Okay, so this is what you're going to get, something like this. This one's all blown up. I blew the diode here out, and I'll explain more about this circuit afterwards. But basically, reverse polarity will blow that chip and blow the board. Okay, so polarity is very important, and that's why you need a meter. All right, as I said, I got way too much wire on these, or lead on these wires, so I'm just going to cut it back a bit. 1 and 2 right there, and solder them on. As we know from our previous testing, the white is the positive, and it's marked on the board which is the positive and negative side. Again, can't warn you enough or stress enough about this. You need to have the polarity correct. So let's put it on. Do one at a time. Over the positive first. And be careful with your soldering iron that you don't melt any of the components on the board. Here we go. I think I need a little more solder on that, so let's get some on it. There we go, that should do it. Let's see what we got. Oh yeah, really nice. There we go. Number 1. Got number 2 in here. I'm probably going to need some more solder on that too. But let's just start. Okay. Let's try it again. Oh yeah, that's much better. All right, so there's a positive and negative. At this point, you could actually test it to see what kind of output we have. So we'll do that next and adjust it to the correct output, and then we'll make the wire the USB-C connector for the actual Raspberry Pi. So I've got it plugged in, got the power supply powered up, and you can see that I'm getting 18.83 volts into the inside side of the actual circuit, and on the other side we're getting 16.78. so it's stepped down, but that's still way too high for a Raspberry Pi. It will actually fry it. But again, we've got this little set screw here. We're going to turn to clockwise. We'll increase the voltage. So let's go all the way up and see what it can do. Now remember, 18 is going in. This is a buck and boost circuit, so it can increase voltage from the input and decrease voltage from the input. So I'm getting 30, 31. So yeah, you see how you have to be real careful with this, because you put this into a Raspberry Pi, it will be nothing but smoke and sparks, right? So again, I just want to show you what this circuit can do. And there we go, 40. So 40.44 is the max, and you'll hear that little screw tick when you can keep turning it forever, but at a certain point it just doesn't do any more, and it just goes tick. I don't even know if you can hear that. There you go. Anyway, once you hit the tick, you've gone as far as you can go. But we don't want 40. What we actually want is 5.25. Now, I know if you look up the Raspberry Pi and the actual power supply for the Raspberry Pi, it'll say 5.1 volts. And I believe it says 3 amps anyways. But I'm just, again, I know one thing for sure, and that is USB at USB 3. The standard for that is 5.25. Now, why I'm saying that is because when you put this voltage through a Raspberry Pi, the 5-volt rail is directly connected to the power source. So if it's not 5.25, then your USB ports won't get 5.25. Now, I also know that the Raspberry Pi can take up to 6 volts. Now, I wouldn't want to test that if I were you, because the PIMIC, or the power management IC, that's the maximum voltage you can take. I would not want to go anywhere near that. So I'm just going to 5.25. You want to play with the voltages, that's up to you, and I take zero responsibility of what happens to any of your equipment, using the information I'm giving you on this video. So as you can see here, I'm too far. Let's go all the way down. And at the very bottom, you can see that it takes it down to 1.276. So excellent little circuit. I actually used the same circuit to power up the camera, and believe it or not, it's much quieter. And by quieter, I mean you don't get the noise that you normally get with the other power supply I have, which was a purchased one, through the microphone. So let's go to 5.25. That's where we want to be. There we go. And this is kind of tricky getting it at 5.25, but again, we're just going to get close. You don't have to be exact here. I'll show you how to calibrate the output from the USB port after we're done making the USB-C cable. So, oops. There we go. And there's no load on it, so this will change once you put the load on it a little bit anyway. There we go. Close enough anyways. I'll mess with that. I'll keep it at 5.144 for now. Again, we're going to calibrate it once we connect it to the Raspberry Pi. But beauty about this board is that this voltage on this side can be anything from 5 volts on up to 40. And I've tested it all. And I'll show you my tests on this board after we finish building this circuit. And, at the end of the video. All right, with the USB to USB-C cable, I like the bare cables better because they're easier to cut, easier to manage. You see these braided ones with the braided outside colorings and stuff. It's kind of a mess, and you got to basically deal with this piece of the wire, which is the outside fabric or whatever they use. You can cut it off, not a big deal, but it's just a hassle. And again, the beefier the cable you can get, the better. At the dollar store, this is basically, your regular dollar store cable. And, and I keep the lengths short because long lengths lead to power loss and what I call sag, or power sag. In other words, you're going to lose the more current you put through the wire and more voltage or load you put on that wire, the more energy you're going to lose to the wire itself. So the thicker the wire, the better, basically is what I'm saying. And the shorter the wire is better. And there's a calculator to figure out how much you're going to lose on length. And I'll put that at the end of the video as well. But again, let's just cut this off. And we want to cut these pretty short. On this side, it doesn't really matter much because I'm going to use this as a testing cable, and you'll see why. So I'm going to cut it pretty short because I don't want to lose anything through it. So I'm going to cut it over on this side. But you probably won't even have to do this. But you could make your own testing cable and calibrate to help you calibrate the Raspberry Pi. So yeah, cut this cable short like this. Okay. So this is going to be our testing for cable for the USB port. Okay, right there. So that's that. On this side again, same deal. This is USB side. You want to cut it short. That way you don't lose that much through it, but not so short that you got nothing to work with as far as soldering goes. Okay, so let's right around there. Should be actually right around. Yeah, we'll go there. What the heck? We know it's cut it shorter later if you think you can do it. So anyways, I've got about 3 inches, 2 inches, about 7 or 8 centimeters, I'd say. Anyway, let's cut it. All right, and it flies off. Now we have that, a USB-C cord. And now what's important here is that, we need to figure out what the polarity on the inside wire is, right? And the way you do that, again, is with this wire. We're going to strip it back and expose the wires, plug it into a USB source, and then check the polarity coming out of the end of the wire. Why? Because polarity is king. If you do polarity wrong, you'll do this to your board. You'll fry it like I did here. And that's on the input side. And if you do polarity wrong on the output side, you will damage your Raspberry Pi, probably irreversibly, because the Raspberry Pi does not have reverse polarity protection because they figured they didn't need it, right? Why would they? The USB-C wire is, assumed to be correctly wired up. So let's strip this back and find out what the polarity is. All right, there it is stripped out, and you can see that there's 4 wires. That reason for that is 2 of them are data cables, and 2 of them are power wires. So I'm assuming the red and the black are the power wires, and the green and the white are the actual data cables, and they're thinner too. So I'm assuming that's going to be the case, but that's an assumption. So we're going to test these out and see what we get. All right, I'm going to use a USB power pack, battery power pack here to test the voltage on this. Use whatever you wish. You can use a wall charger. I wouldn't recommend doing this with a laptop because there's a chance you might short these, but don't do that. So yeah, maybe. I mean, again, any USB source will do. Just be careful not to short the ends because I don't know what that's going to do to any of your equipment. I'm pretty sure this Anchor power source or power pack can take it, but don't need to test it. So I'm just going to hook up my meter here and we'll test out which one's positive, which one's negative. I'm pretty sure I'm going to get it right. All right, and the assumption was correct. Red is positive, black is negative on that wire. So that means when we strip back the USB-C cable, we'll get the red is positive, black is negative situation. As you can see here, 5.16 coming out of the power pack. So and no negative symbol there. So again, we got it right, and let's get it the USB-C side connected to the power, the buck boost converter, and then connected to the Raspberry Pi. All right, I got a little groove around this wire here, and this is USB-C. So I'm going to just pull the insulation off here. Hopefully it'll come off easy. Looks like. Okay. Maybe not. There we go. And there's our 4 wires again. We've got the red, the white, the green, and the black. We're going to trim off the green and the white because those are data cables. We know that. And, I think I made this a little short, but I'll use it anyway. I recommend probably going twice this length, because you want a little bit of flexibility from the power supply to the actual Raspberry Pi. But for this demonstration, we're okay. But yeah, I would go with at least twice that length. Okay. So let's cut off the excess wires, green and the black. We don't need them. There we go. Then we're going to strip back these 2 wires, tin them, and then solder them onto the buck boost converter, the XL6019, and I'll show you that next. Alright, I got the wires tinned and we're ready to solder them on. Positive to the positive pad, negative to the negative pad. Let's do that. So that's it soldered on there. Let's do a power up, test it one more time for output there before we plug it into the Raspberry Pi and calibrate it from there. All right, verification. We've got the positive and the negative in the right place for the USB-C cable. As you can see over here, we don't have a negative sign in front of the voltage, so we've got positive and negative correctly. I got the red lead, which is the positive lead, here to the white alligator clip. Same on the other side. Same on this side. So we got verification of polarity. Polarity is extremely crucial. It has to be correct. Double check it, triple check it. Just make sure you get it right. And by the way, guys, you know, on the board that I did blast, right? Just so you know, I did that on purpose. I reversed polarity the input to this board just to see what would happen, right? And obviously, not good. You see the piece of that chip missing there. It just blew off, and there were sparks as well. So yeah, polarity, very important. All right, let's power all this up and see how it works. Power on. Lights are flashing. This is good. Power over there. 5.128. Appears to be booting. I've got, I'll show you the screen of the machine booting too. I'm capturing that as it boots. So, so far so good. And when I get to the screen, yeah, there we go. Booted up. And Wi-Fi is connected, so we're good. Let's open up the browser, see what we get. And as you can see, even at 5.12, whatever, you know, it's solid, it's good, right? Now, again, there's going to be some, you know, variation as the power gets consumed on and off kind of deal. But right now, looking good. And I'm going to show you all how to calibrate this to 5.25 using the little piece of the USB connector that we cut off the other side of the USB-C. And we'll do that next. But right now, looks like we're good. Let's test something. Let's go somewhere here. Well, I got nowhere to go. I don't have a keyboard plugged in right now. So basically, it's working, but let's just reboot. Let's shut it down. And okay, so I'm going to shut it down, and we're going to, you know, calibrate the power supply, this power supply here, to 5.25, which is what it should be coming out of the USB port, and we'll go check that too. Okay, so let's just shut it down and continue from there. All right, got a lot going on here. What I've got is this meter here is checking the output from the buck boost circuit directly out of the pads there, and this meter is checking the output from the USB port. And what we want to do is get 5.25 out of the USB port. That's what how I calibrate them. Let's reset those so they don't go off, and let's just power it up, see what happens, and then we'll change it by moving that little adjustment screw on the circuit. So let's plug it in. There we go. And 5.14 over here, 5.11. So you're not losing a lot, you know, pretty close. Okay, so the Raspberry Pi is booting up, as you can see on the screen. Well, maybe not. Let's see. There we go. Capture it, and my desktop is up. So next, what I'm going to do is adjust the voltage coming out of here to give me 5.25 on the USB port, because that's how I calibrate these things. Now you can do whatever you like. I don't suggest going over anything over 5.75 into the machine, or you know, through that port out of the USB port. You're just pushing it too close. I wouldn't even go to, you know, oops, that's way too high. Let's go back. 155. Got it, more or less. Now, look, 5.29 over here, 5.26 over here. It's a 0.3, 0.4 difference in voltage from this circuit over to it. Pretty good, right? Only losing 0.4 from the actual circuit itself, the boost buck board, to the USB port, right? So there it just varied a little bit. Now that could just be the, you know, Raspberry Pi doing whatever it's doing, probably checking for updates. But it's on Wi-Fi, it's connected, working just fine. No low voltage warnings on the screen or anything like that. I can make a low voltage warning come on the screen. Let's do that. Let's go move it down to get, I think 475. It'll start giving me a low voltage. Maybe not. A little more. 460. Still no low voltage. Amazing. I wonder what the limit is. I keep going. There we go. It's 4.5. So let's, I got the low voltage on the screen. Hopefully I've captured that for you guys. Let's go back up. And when we hit, when does that go away? I thought it was 475. Just took a while for it to come back up. Please check your power supply. Okay, well, there it went away. So again, you can vary it. Use as little, as much as you want. Again, don't go over 5.75. Or, you know, like I said, I'm not responsible for any damage you do or, you know, happens because of what you did following my video. So you're on your own. This is educational purposes only. Zero responsibility. Okay, so there. We're almost at 525. Oop, there we go, more or less. You know, you're going to float a little bit. There we go. Go a little higher. And I don't know if, well, here we go. Yeah. So again, close enough for me. You know, it varies a bit because of, you know, voltage use and, you know, line sag on these little cables and so on and so forth. I've got a better USB port tester, I think. Let's see. Yes, I do right here. Let's try this. Pull this off. Now this has got a really small display. And we'll put it, oh, we'll just put this under the back of it. There we go. And it's saying basically exactly what this is saying. Yeah, it's very well calibrated. Maybe a little lower. Maybe a little slower, who knows, right? But there we go. And if you got one of these, you don't need the meter to check it, but there, another way of checking it. But regardless, there we are, calibrated. We'll go down a little bit. Just a teeny bit. And like I said, you don't need the second meter. You only need 1 meter to check the voltage out of the USB port to calibrate the correct voltage. Start low, work your way up, right? Very close, right? Again, don't want to spend all day doing this, but there we go. Tweaked up and connected. Now this is very basic. We've got no power switch, no nothing. It's just power going to the board, power coming out of the board to USB to the Raspberry Pi. But as you can see, working just beautifully. And let's shut it down. And then you know, the rest of this video I'm going to show you, you know, basically testing this board. I actually put 3 amps through it. It will survive that. It does it, no problem. And I'll test it again here, and you'll see that. But I'm not putting 3 amps through a Raspberry Pi. No thanks. Though the power supplies that they ship are 3 amps. This can do 3 amps. So if you need it, it's there. I've never been able to get that much power to be drawn from the Raspberry Pi, and don't know how you do it, but I'm sure there's a way. So here I'm just going to shut it down. And you know, again, I'll go into some of the testing and show you the parameters and the specifications. But basically, that's how you make this little power supply. And with this, another bonus here with this buckboard, just so you know, this voltage can be varied anywhere from 5 volts all the way up to 40. So if you're on a battery system, this is a really good way to power a USB-C power for your Raspberry Pi, robotics, automation, anywhere where you're running on batteries and the voltage varies. Very good solution. All right. So yeah, outside of AC power to DC, DC directly, these are beautiful devices for that. And by the way, with the 65 watts that I have, I could actually run 3 of these off the same power supply. So, you know, much more efficient than $13 a power supply just to buy 2 more of these and hook them up to the same power supply. Here's a collection of my power supplies for Raspberry Pis, and well, the one we just built right here is on top. This is one I soldered XT60 connectors on, and some I think 16 gauge automotive wire too, which makes it the one I use for testing the most, because short wires, thick wires, and I don't lose any power on it. So when I'm going to load test the Raspberry Pi with this circuit, I'll be using this one because it's just easier to connect to everything. This is one I use here on my Raspberry Pi. I think this one's the 4 gigabit. And notice that I have a rocker switch for on and off. And with the rocker switches, make sure you get, when you order them, and I'll put links to the rocker switches in the video description below, make sure you get the ones with the actual tangs that clip on, because soldering to the rocker switch, when I did it, I melted the switch. So it's much easier to solder onto these connecting tangs here, and then just, you know, clip them onto the switch without putting any heat to the switch at all. I did get away with it once here on this one. This is for my 8 gigabit, and I put some heatsink material on there. I'm not sure whether it does anything or not, but it seems to take some of the heat off of it. And I put some on the bottom as well. Again, power switch. This is one I successfully soldered to, but again, it did melt it a little bit. And on this side, I noticed that, and I put the actual connector onto it and soldered the connector instead of, you know, soldering to the tab on the rocker switch. Again, works great. And this one here, this is my camera power supply, and it's one of these circuits. But what I did is I put it in heat shrink, and heat shrunk some tube around it. And if you can see right here, I have the little adjustment screw right there. So I cut a little hole through the actual heat shrink tubing, and now I can adjust the voltage on my camera to what I need. This is 6.7, as you said, minimum 6.7 volts, maximum 8.3. So I know basically I've written that down there. And obviously I'm not using it right now, but normally when you see me on the camera, this is a power supply that's powering it, and it's one of these circuits, you know, the 601. The XL6019 circuits that I show here, again in the video description below. And XT60s, by the way, are total overkill on this. An XT30 connector would do fine, or any, you know, reliable electronic connector that can take 3 to 4 amps will work just fine. But there we go on all the different variations and flavors you can do. Now there is one more little trick with these to turn them on and off, and I'll show you that later in the video, because the circuit itself is this actual IC has a pin on it that if you drive it low, it will turn the power off to the actual whole circuit. So I'll show you how to do that as well, and then you can attach a power switch to the low point and then turn it off that way as well. It's just a neat thing to know. And if you were controlling it electronically with a small relay, you could do that without having the actual switch. But either way, you know, both systems are effective, and no switch at all is effective as well. And you know, I just use the power switch on my power bar for the Raspberry Pi as well. All right, here's the various power supplies that I got for my different power projects here. You can see the camera power supply here is run by a Sony PlayStation AC adapter. Okay, so you know, just so you know how variable, you know, you don't have to really use, you know, there's no specific power pack, just one that gives you the amount of voltage and that's acceptable, and amperage that's acceptable, and wattage that's acceptable. This is an old Toshiba laptop power supply. It's probably about 16 years old, and this is just some random wall brick that I found in my closet, and I plugged it into this one here, and it powers my one of my Raspberry Pis, no problem at all. So yeah, and I've also actually powered one up with a 12-volt car battery just for fun. Okay, so yeah, it's you know, you're not tied into any specific power supply. You can use it just about anything that's DC and has the right amount of amperage to it. You know, so again, I'll show you the Ohm's law calculator in the video description below too. But really, as long as you can multiply the voltage by the amperage, it's over 5 volts and you get 20 watts plus, it's good. And going deeper here, this circuit is not fuse protected. I would say it's diode protected, okay? See this diode right here? That is called an SS36. And it will be the thing that blows if you overload or load this circuit too much. This will, basically go, okay, I can't handle it anymore, and go pop. So, but that's the only thing that's going to go on you, is just that, if you overload it on the output side by maybe drawing too much amperage or too much voltage or whatever. Basically, if you tax this circuit, this is what's going to pop, and it's called SS36. And I've gotten them and replaced them. And how do I know that? I've blown them many times. Let's see if we can get this to focus here. I've got a package full of them here. You'll see that the SS36 is a 3 amp, 60 volt diode, Schottky diode. And again, it will blow, right? But they're very cheap. Again, links in the video description below, just in case you blow one. The other thing you got to watch out for is this little component right here. It is very fragile. It's easy to snap one of these. Snap this component. It's not coming to me right now what it is, but it's basically the same as these. It's a coil. You can see that it's a coil right there, and it's quite fragile. So if you hit that hard, you'll snap it, and then well, you're kind of done once you've done that, unless you want to unsolder it and get a new one and put a new one down on there. But those are the things that are going to go. It's going to be this diode if you overload it, this coil if you hit it too hard, and of course this chip if you reverse polarity on the input. But then you're probably going to just blow up just about everything on it. So I wouldn't bother, like I said, at $3, these are about $3-4 a piece. So, you consider how much you want to fix them. But if you're going to be testing, definitely get yourself some SS36 diodes. So when you do blow them, you've got something to, instead of replace, you don't have to replace the whole thing, just replace the diode and you'll be fine, right? And again, we'll do some load testing on it, and I'll show you how it all works and, the heat that comes off it and so on. All right, for load testing, I'm going to be using this power pack. This is an HP printer power pack. It's 32 volts at 1.5 amps. And if we do the math on that, you'll see that it's 48 watts. So let's go back and go here. So 1.5 times 32 volts, 1.5 amps times 32 volts equals 48 watts, which is twice the power I need to do this with. The reason I'm doing that is because this power pack, has my XT60 connector on it, so it will mate with my testing board, no problem at all. And my ammeter over here as well, so I can show you all the results. And also to show you that, again, power supplies are plentiful. I got this one out of the garbage, actually. Somebody threw a printer out at the side of the road and destroyed it in the process of doing that, but the power supply was still good, so I recycled that, retrieved it, and now I've been using it for a very long time as a reliable power supply for projects like this. So again, you can use just about anything you want, really. I've got a large battery pack, a 16-volt battery pack that I've used to power these up. It's the list is endless. So for robotics, this is an excellent DC power source, or converting power boost board for anything under 3 amps. And again, if you're making a robot or something, very useful to have one of these to power your Raspberry Pi and the servos or anything else you need to power, because it's variable. It doesn't have to do just 5 volts or whatever, okay? So let's put this together, and we're going to stress test the actual circuit itself. All right, we've got 31.42 volts going into this. That's from that HP power supply with the XT60 on it. It's going into this boost buck, and it goes from that into my ammeter. This is the actual measuring unit. This is the display for it. And from there, we're going to a constant current, constant voltage charger. And from there, we're charging an 18650 cell right there. It's the only way I could get this load to actually do 3 amps at 5 volts. So I'm sure there's other ways, and I got to get a load tester and, you know, buy one of those too if I'm going to do more of these videos. But this works. So here we're just going to turn it on, and you're going to see what an extreme test is, because I'm going to torture this thing. And if I blow it, I know it'll just be the resistor, not the resistor, the diode, the SS36 diode that goes. I just have to replace it, and it'll bring it back. So right now we're at 3.58 amps, 85 amps. And let me just stop for a second. And, you know, we started with 526. So it was 5.25. But anyways, 5.26 volts, close enough, which is what we were feeding into the Raspberry Pi. And the whole point of this test is to show you this circuit can deliver 3 amps plus. Now, I don't know how long it can do over 3 amps, and we're almost at 4 with this thing. I'd like to dial it down. I don't know if I can. Maybe I can. Let's see if I can. Nope, that is as low as it goes. So, it's still delivering it, right? So let's see how hot's it getting. Let's see what the highest number I can get off of that thing is. And oops, you can't see it. I'll put it over here. Currently 130. I saw 130. Ooh, there's 151 on it. So I don't know what the thermal cutoff is on the actual IC, the XL6019 from XL Semi, but I don't think I've ever hit it. I think the diode will go before the thermal capacity or the thermal shutoff on that chip will shut it off. I've always seen it power all the way to the end, and then at the end I see the diode just, you know, frying. Now it doesn't do anything. It doesn't smoke or anything. It just stops working. So now we've drawn down the voltage to 4.99, but that would still be enough to keep your Raspberry Pi running without even an over voltage warning. But again, I'd never want to put 3.5 amps through a Raspberry Pi. I think that would be probably a mistake, right? In a circuit, the weakest point will be the fuse. So if the Raspberry Pi can't take 3.5 amps internally, something in there can't handle it, poof, Raspberry Pi will go. So personally, you know, the fact that this can do 3.5 amps, that's cool. And if you know anything about amperage, you know that the circuit has to draw the amperage from the boost spot converter. So it's not like this is going to go to your Raspberry Pi. It can only be drawn from it. So, you know, again, if you wanted to draw 3.5 amps, you could. And it's, let's see how hot it is now. Let's do some more. Ooh, right around. Let's see what the hottest temperature I can get off that. There. Ooh. I saw 225 there for a second. There. So there, 224. And again, it's still running. Still giving me 3.41 amps. Still giving me 4.99 volts. So think about that, right? You're drawing that much energy from it, and it only sags a little bit. Remember also, you know, we've got wires in between, you know, not very long ones. So these are very thick too. So, you know, the 4.99 is probably happening pretty well at the board. Let's check it at the board. Let's keep an eye on the temperature. Don't want to. Well, actually, it doesn't matter. I would like to see what the thermal cutoff is on it, but I have never hit it yet. I saw just a second. Ooh, 235, 237. No, it's actually, but I got 234 there. Let's check the voltage at the output and see what we're getting from the board itself. We know it's getting 31. Let's see what we're getting on the output. There we go. I checked the battery. Battery's not too warm, so it's okay. Yeah. So this 5 points, I'm getting, the board itself is giving 5.7 volts out still. So I mean, you know, now we're down to 3.1, 3.11 amps, and you got to wonder, you know, how much. There is a current limit on this board, and there is an overcurrent and a thermal protection circuit in this chip itself. So let's see what we're at for temperatures on it. See what we can find. Woo, 246. But as you can see, it's still giving out the amperage. Now also you need to understand this is constant current, constant voltage. So what it's going to do is basically step the voltage down as the battery reaches its terminal voltage. The amperage down as the battery reaches its terminal voltage. And seeing that its terminal voltage is actually 4.2 volts, I'm overcharging this battery, but it's an old one and I'm not really worried about it. This whole point here is not to charge the battery, but to show you that this circuit can deliver a lot of power, right, at 5 volts too. All right, so, and if you've been keeping an eye on the wattage, you see that we never really hit that high wattage. Okay, 243 on the circuit. Remember, there's no heatsink on it. I'm kind of worried it's going to melt my meter. 250, right? Watch that. Ooh, it is hot. But, currently being cooled mostly by the air around it. And as you can see, it has not fried the circuit. So I don't know. I'm worried about the battery right now. Let's see where we're at with the battery on. Yeah, it's, what are we getting there? 94 degrees. So, but I mean, this circuit is getting quite warm. But even as warm as it's getting, and one of the things I couldn't get off the spec sheet on that XL6019 was that the actual thermal cutoff temperature. So obviously it goes quite hot because we're still delivering power. All right, now if I stop it, let's do a stop. It goes right back to 5.21, and it was 2.6, so it's probably the heat that's affecting that output, but still, right, very stable. Let's hit it on again. 3.26, 16 watts. So, it's approaching. We're about 4 watts short of what it could be. I could increase the current here and see, just stress it. Yeah, I know. Here you go. It times out, my meter times out if you leave it alone for too long. So let's go up in amperage. If it will, I don't even know if it will. Because, again, the circuit itself is not going to let me do it. No, it's not going to let me do it. So I'm at the maximum amperage. And like I said, the point was to show you that it can do the required, 3 amps. And it certainly can do that. Let's try a different battery. Take that one off. Put another one on. Yeah, that one's a little... That one probably has more of a charge on it. I need a deader one. This one, let's see. Nothing on that. What the heck? Shut it off? No? Oh, that one's fully charged. Yeah. See, the circuit knows. It says, hey, yeah, you're giving me a fully charged battery here. Can't do anything with that. There we go. Yeah. So I'm running down on batteries that are that dead. Let's try something else. Hopefully, I don't know if this one's going to fit. We'll try it. But basically, there's the test. It does 3 amps and plus. Actually, it does even more for short periods of time. There, 3.5, right? 3.54. And this battery is actually circuit protected internally, so if I go over the limit, it'll shut itself down. Yeah, so there's 17 watts. Again, way more than enough, right? And, okay, I'll just leave it there. See what happens. And what's my temperature? Let's check that out. See, this is, like I said, we're into the mad scientist portion of the video. But, yeah, the whole point is to show you this is an awesome power supply for a Raspberry Pi. 233 on it right now. So, it can use any voltage. So if you've got a robotic application, or like, let's say you're off grid, you're in a trailer out in the woods, well, and all you got is 12 volts. So this will power your Raspberry Pi. You're on a boat. It'll power your Raspberry Pi, whether it's a sailboat or a cruising boat, whatever. Motorcycle, car, you name it. Solar cells, it will do it. It just, as long as you don't go over 40 volts, and I've taken it to 40 volts without any issue at all. It will take 40. I've done it. Let's see where we're at now. See, again, my load problem, right? Yeah. Let's see what we get for a temperature here. Highest temperature I can get. Yeah, infrared, not the most accurate. There we go. 239 right now. So yeah, there you go. It didn't even fry. I have fried them, but you had to go a lot higher in amperage than what I'm currently at. Probably closer to 4 amps for any period of time, and you will fry it. But holy cow, you don't want to put that. If you ever put that much load on your Raspberry Pi, more than likely the Raspberry Pi will be the thing that fries. So again, I don't suggest you do that. Now I'm going to take a Raspberry Pi and connect it and test to see how much actual wattage and amperage I can draw from this thing. And I never ever got anywhere near this. This is much more than I ever could. Okay, so I'll show you what I got to do just to crank it up. All right, let's load test it. Currently it's just idling. I've got the video out to my monitor. Power in through my ammeter. You can see the results right here. Hopefully that can be read on the screen. I got 5.250 on the USB port on a USB hub already plugged into one of the ports, so I can plug a lot in there. I've got a wireless mouse and a wireless keyboard plugged into that hub as well. I don't know if you can see them there through the cords, but they're right there. I still got a port left on that USB hub, and it's unpowered, though it can be powered. That is an unpowered hub. Other than that, I've got Ethernet plugged in currently, and it's connected. So let's just start plugging stuff in right now. 0.62 amps. I've got 3 laptop hard drives, and these are not SSD. They're conventional spinning drives, and if you know anything about those things, you know they suck up a lot of power. And if you have one in your laptop, consider changing to SSD. Much lighter, much faster, and much less power. All the way around, better. So let's plug one in. I just plugged the 2 terabyte drive in. You see the light flash in there. All right. Screen just popped up for showing me the contents. I don't need to see them. Just leave it up and let it spin. So once it's done blinking here, maybe I will initialize it there. Give me a second. Get my mouse and hit OK. There we go. Drive comes up. Looks good. So we know it's working. Solid light on the drive. Let's try one more. And again, 1.11 amps. Voltage is 5.31 at the ammeter, but 5.18 on the USB hub. So, again, limitations on USB ports on the Raspberry Pi as far as how much power they're going to give out. Let's try a terabyte now, giving us a total of 3 terabytes in total. And it says, gave me a little complaint about removing a drive. Let's see if they come back up. I've got a blinking light here. I hear them clicking. Well, there's one. Came up on the screen. Ooh, not good. So I'm starting to suffer on power here. So 2 spinning hard drives. Maybe it's just too much being drawn from those ports. But as you can see on the power supply, and we got on the USB port. Oh, see that? So it's limited there on how much power you can get out of the USB port. Okay, so it's not the fault of the power supply, because if you look here, you see it's still a 5.25, 1.42 amps. You know this thing can do 3 plus. So we're not there yet. Let's see what we got going on. See, maybe it did do the 2. Let's see it. Okay. Yeah, it did do the 2. There's 1. Let's see if the other one's up. Nope, just 1. Yeah, just stabby back up. That's it. Okay, so it won't power the second one. So this one, let's take this 1 terabyte out. Let's put another 1 TB. Maybe we got a little bit less power on the next one. Who knows? Maybe I'll unplug the USB hub here. We'll see what happens. But there's a second one. Yeah, it just doesn't like it. Let me pull the hub off and see if that gives it enough power. As you see, there's 0 because the hub is where I got the voltage coming out from. Blinking lights and no power. Just doesn't like it. So it has a limit on USB ports, but I don't think that's a limit on the power supply. As you can see here, we're fine on power. Let's plug that hub back in. Okay. It's trying, but it's just not going to do it. Okay, let's try a different drive, see if we can get a different result. This is an older drive, probably a 500. Let's plug it in. Making a funny noise. Okay, let's take this one out. Maybe it's the 2 terabyte that's the problem. Well, that one spun up. It's giving me an error of some kind, and you guys can see that, I'm sure, because I'm going to put it overlay on the video. Let's unplug it, replug it back in. Here we go, but you know, you can see the wattage and the amperage there. I don't know if it took it or not. Let's find out. Does not look like it. No. Oh well, let's try the second port downstairs. My issue might be with the drive. Let's see. It's not plugged in all the way, maybe. Okay, that one went. Wasn't plugged in right inside the case. Okay. So we got 1. Can we get 2? We've got 2. So it can do a 1 terabyte in this 500 gig. It's power distribution to the USB ports, obviously. But as you can see from the power, right? We're not dead. We've got 525 coming into the ammeter, and that is adjusted to 5.25 on the output, and we're still at 5.1, which is what the standard Raspberry Pi power pack would actually supply to you from the wall. So, you know, this is doing okay, right? Running 2 hard drives. Let's plug more in. How about another keyboard? Let's do that. Yeah. There we go. Got 1 keyboard here. This is a backlit keyboard. Plug it in. I'm running out of room. There we go. Put it in here so you can see it. Maybe I'll switch one light off here. Yeah, you can see that it's backlit. It's lit. Still working. 1.144 amps. Like I said, I've never figured out how to overload this thing. It's just, you know, not enough. I can't draw enough power out of it. Let's plug in a second lit backlit keyboard. See what we get. We're running out of USB ports, actually. That'll be the last one. Let's put another one there. It's tough. There we go. There's another backlit keyboard. Here's the other one. Right there, as you can see, 2 backlit keyboards. And now we're down to 4.99, 5.0, but we haven't got a voltage warning on the screen yet, and both hard drives are still connected. So 1.67 amps at 8.56 watts, or 8.8 watts now. Now, let's do a stress test on this CPU. So we're going to run stress here. Oop, there we go. Now we're having an issue. Yeah, it's not liking that. Just the USB ports can't handle that much output. So let's just take one thing off the USB ports. See if that helps. Come on, bring it back. Once that happens, take one out. So yeah, I mean, you know, let's get real here. We're pushing this a lot. We're sucking a lot of power from USB ports. That's the problem. Let's plug it back in, see if it comes back. Appears like it has. Just doesn't like it. I've got too much on those ports. So I'm going to unplug the keyboard and see if it comes back. Okay. Get these keyboards out of here. Excuse me. This is definitely stressful for the machine, but again, that's what we're doing here. Do I have two? Let's see. Nope. And I've unplugged my keyboard or mouse. There we go. Back. Alright, so now we got two drives working again. So the problem here is not the power supply. The problem is the USB port. You know, there's only so much it can supply. Okay, so because you know this is still giving it 5.24. So let's do the stress test on it. Yeah. Wait, and see if we can get more power being drawn out of it. I'm gonna need my keyboard. Here we go. Want any of that? That's what we want. There's the stress test. And we're up to 10 watts, almost 2 amps. Oh, look at that, 2.21. That's how you get the power coming up. All right, there's a removable drive inserted, okay. So all those are working. Yeah. There we go. It's pushing it. So yeah, there's about all I can do, and as you can see, it is, you know, pretty robust in a sense. Let's unplug the drive that doesn't look like it's functioning right now. Plug it back in. Still, we're not below the level on this. All right. Do I have two drives plugged in now? Yes, I do. Okay. That's that. And the stress test still going over here. Don't believe I have the second drive mounted. Let's try the second drive down here. Still trying, but as you can see, you know, it's handling. Oh, there it is. There's the second drive. So we've now got two drives, 1.5 terabytes of data, disk drives in there. Again, we're really pushing it. 9.79 watts, 1.89 amps, and as we know from the tests I've run, this thing can do 3, so it's not being limited by that. I think at this point I'm just running out of things to connect to it to suck power from the Raspberry Pi. Maybe if I had a camera or something on the GPIO, drawing power there, or the PO, whatever, like, power over Ethernet. I'm not sure, but currently a second monitor maybe. That's as much as I can draw out of it. But you can see here, we're still at 5.03 volts on the USB port, 5.8 volts coming into it. So that could be adjusted. I could give it more here on the power pack and bring it up to 5.25. Not the way you should really do it, but I mean, again, we're calibrating. If you're running this stuff all the time, it wouldn't be a bad thing to do. There we go. Oops, ooh, a little high. Bring it back down. Bring it back down. There we go. Okay. Ooh. It's tricky right around that spot. 7.9. Again, it's not that far off. It's, this is 1/100th of a volt. So there we go. Now get that up to, okay, so geez, it's like I'm going to give you 3 or 5 or 7, right? Okay. Ooh, too much. I'm using my finger too. Find my little tool and do it right. Okay, so okay, I'm leaving it there. That's pretty close. Let's plug in another drive. See if it will do a third drive now that we got 525 going to the USB port. I'm hearing them clicking. Just can't do it. It won't do 3 drives. But we'll do 2. There we go. Right back up again. So boosting the voltage helped, I think. I've got 2 drives there, no problem. There we go. And you can see the temperature of the CPU is 77.4. Control C that. Try this again. There we go. Wonder if we can run that test twice. Let's try that. Nope, that's not going to do it. There we go. Copy it. We'll try this at home, kids. There we go. Yes, I'm running it twice. Didn't make much of a difference though. Still, the watts are 9.864 watts, 1.80 amps, 528 on the voltage. Drives are running nice. There we go. So yeah, there's your stress test. I can't make it draw any more power than that. That's basically it on that. I'm going to show you a couple more things about this circuit, which are kind of cool. And then we're going to wrap it up. All right. One of the neat little features on this circuit is right there. You look right there, you see that little circle, that little solder point, and you see the EN next to it. And that's short for enable. It goes to pin 2 on the IC. And pin 2 to the IC usually is driven high, meaning that whatever voltage you put into this card will be on pin 2. So in other words, in my case, in that that last circuit I was showing you where we were testing the Raspberry Pi, I was driving at 31, so 31 would be here. But if you're driving it at 9 volts, 9 volts will be here. The whole point here is when that's driven high, this integrated circuit turns itself on. So it senses a high voltage here, it turns itself on. Now, if you drive that pin low by shorting it to ground, right, basically from here to here, that sends a signal to this chip to turn itself off. And effectively driving this little pin down here, or this little input to this card to ground, will shut this whole circuit off. But it won't short the inputs. You think, oh, 31's going to it. When I short it, it's going to short out the power supply. It won't. It'll just turn the chip off. So I'll show you that in the next slide. So we have 31 volts coming into the circuit, 5.18 volts coming out. I'm not driving anything, but it's just showing you that the circuit is active. The enable pin is right there. And what I wanted to show you is, well, let's first see how much voltage is on the enable pin. It should be more or less 3.14. Sorry, 31.4. So let's see. Yeah, I just took the meter off the input voltage, and I'm going to put it on the enable pin. So almost the same, 31.09. So it loses a little bit through the circuit. So as I said, that pin 2 on that IC is being driven high by default on the circuit. And I've got another alligator clip here connected to my ground, and I'm just going to take ground and short that enable pin. So basically driving pin 2 on this IC down to ground. So let's do that. And you can see that instantly I get, well, almost 0 volts over here. So it's driven down to off. There we go, off. I guess the capacitors had to drain a little bit, but it does nothing to the incoming voltage, right? So the IC has got an internal switch that when you drive pin 2 down to ground or 0, it shuts off the IC. So if you wanted to set up a switch, you could just put a switch between ground and this enable point here, or this solder point here, and that would shut the circuit down. And when you open it back up again, it would automatically go back on again. So that's a neat little feature. Not sure what you'd use it for, but if you had some sort of control where you could, drive that low, electronically, that point would be a perfect place to shut this off at. I just use a switch on the positive lead, and like one of those rocker switches, and that's more than good enough for me. So that's that point. Now, the other thing too is that, again, as I warned you before, these inductors, just be careful with them, these little coils, especially this one. These are tough as nails, like as far as I can tell. But this one here is prone to breaking quite easily. And you can see that I've been playing with the circuit quite a bit around this area because I blew that diode many times testing it out. So that is the SS36, and that's not the original, obviously, from the poor soldering job that I did there, but it's functional. Anyways, be careful certainly with that coil right there. So next, I'm just going to show you how well it can drive the voltage through various inputs, and what the lowest voltage you can go to, plus well, that's basically all you need to know about it, and then we'll wrap it up. All right, I know this looks a little busy, but this is what we got. Buck boost converter here. I'm using it to vary the voltage going into this buck boost converter, which is powering the Raspberry Pi. Let me turn that off. And basically a 5.25, as you saw here on the meter. And what I'm going to do is vary this all the way up as high as I can on this boost converter to show you that this one just continues to give the power it should to the Raspberry Pi, regardless of the variance in voltage. I believe it can go down to 4 volts. I wouldn't take any lower than 4 volts because the circuits start getting a little crazy at that point. By crazy means they're not reliable below the 4 volt limit to give you the constant voltage that you require for the Raspberry Pi. So warning, don't go below 4. Okay, so let's take it down to 4 here. Like I said, I got right here, I've got 5.29. That's what this is measuring here, going to that buck boost converter. And you can see voltage here for the Raspberry Pi and that it's booting. So let's take it down and to variable voltages. You can see that it stays more or less solid over here, and this is the output from the buck boost for the Raspberry Pi. There, I got it down to 4.63 and 4.45, 4, 4.6. Like I said, I don't want to go any further than that because, like I said, I know it starts getting wonky. Oop, there's 395. So again, pretty far down, but that's as far as I want to take it. You know, again, 3.9 volts running 5.24, solid. Let's go back. Let's go all the way to the top, which is around 35 volts on this. So if you got a variable voltage situation like a battery, solar cell charger, generator, car, boat, whatever you have that's giving you DC, you can see here that this thing keeps the voltage, you know, stable no matter what your input is. And you can see that this is actually going to be acting somewhat like a surge suppressor because, you know, you can spike the voltage like boom, right? It doesn't do anything over here, right? So let's go up, 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 up. We're almost at car volt. Well, actually, we are car voltages at 12 volts. That's a lead acid battery in a car or a boat. Keep going, keep going, keep going. And they go to 14.4. So we're still in the car now. Ooh, we're over 14.4. Now we're getting into RV batteries, which are about 24 volts. Sometimes, depends. Some are 12, depends. There we go. And no problems, just as you can see over here. And you can see that this is a great little circuit for giving you whatever DC voltage you want. There we go, there we go, there we go. It's climbing a little bit, but you know, still, it's only 1/100ths over 5.25. There we go, still good. 31. I mean, that's massive. 32. 33. 34. And stable up, but still. I think 35 is the max it can do. Well, make a liar to me. It looks like it could do 36. And that's it. And then see, you can see that I can turn it all I want now. It just drops off. So 36 seems to be the max there. And yeah, super stable. Let's go right back down real fast. You can see that the Raspberry Pi is still blinking away. It's just fine, as it should be. Take it back down. And like I said, don't take the voltage below 4 volts. You know, I'll disconnect it from the Raspberry Pi when we get to that point, and I'll show you why. Because I don't want to overdrive the Raspberry Pi, and you'll see why I say that in a minute. So let's keep going down. 10, 9, 8. Ooh, okay, so there we are. I'm going to turn off the Raspberry Pi there. So it's going to go to 0. And watch what happens here when we go below 4 volts. Alright. Actually, here. I need that disconnected, the Raspberry Pi disconnected, but the power on to that. So 525, you know, no problem. All the way down here. Keep going, keep going, keep going. 385, still good. 374, still good. See what happened? 34 volts at 3.8 volts. I don't know why it does that. It's crazy. But if I plug that into my power pack, this thing here, this power, actually, no, I can't plug it into that. If I plug it into I put the right connector on that, it doesn't like it. It doesn't fry it, but it just basically says, ooh, error, and we're done. So I would want to put that into anything, you know, like a Raspberry Pi. Let's short that out. Okay, so I just shorted it out, and it just comes right back. But, you know, again, see what happens below 4 volts, right? So that's kind of wonky, weird. Don't ask me why it does that. Let's keep going. And then it just drops off, right? So that's, you know, but right in that range, right there, see that? It gives crazy power. No idea why. But, so, warning is don't take it down below 4 volts because you're going to have an issue. Or you may have an issue, but I don't want to test it out to to find out if I'm going to. I just know not to. And besides, most of my power packs are, 8.5 volts and higher, so there's never going to be that chance of that happening. And if you're using a stable power supply, that never is going to drop to that point, you're safe. But if it is, maybe have a shut off like this ammeter or this circuit here can shut this off. I can have an under voltage, what do you call it? A low voltage priority and LVP right there, low voltage, and it will power it off below a certain voltage, right? So, but again, not an issue for anybody making it the way I showed you to make it with a stable power pack. It's not going to do anything to your Raspberry Pi. Just be careful below 4 volts. That's it for my video on the XL6019 boost bot converter being used for a Raspberry Pi power supply. I use it actually, guys, on 5 different Raspberry Pi 4s that I own. Yeah, I know, I got lucky. I bought them before before they were hard to source. But and one of them is a DNS server, basically network device that's been on for over a year. No problem with this powering it up that whole time. Okay, so and on top of that, this camera that I'm currently using is right now being powered by one of these. I showed you the circuit earlier in the video, and my camera is worth over $1,500. So obviously I trust it, right? Because if I didn't, I certainly wouldn't plug it into such an expensive piece of equipment. And yeah, that's been working great for a very long time. So very happy about that. Okay, so if you like this video and it helped you out in some way, do me a favor, give me a thumbs up at the bottom of the video. Also, if you like my content, please consider subscribing. As part of the subscription process, you'll get a bell icon. Click on the bell icon and you will be notified every time I put up a new video, and then you can watch it whenever you'd like. Also, in the video description below, I'll put links to all the stuff I used in this video, including the beautiful little board. They do make one of these with a different IC on it, and the IC is XL6009. Don't think it's the greatest. I think this is a better board. Personally, I do have a 6009, and it didn't work the greatest on my Raspberry Pi 8 gig. Okay, but these have been flawless in everything I've used them, so go with the XL6019. Also, those links in the video description are affiliate links, so basically use those to buy your stuff. A couple of reasons. Number one, you're supporting my channel when you do so, and again, they don't cost any extra for you to use them, just going straight to Amazon and eBay and clicking and finding and clicking it. Number one. Number two, you get the same stuff from the same sellers that I bought it from, so you're guaranteed to going to get the same board that I used in this video. And again, greatly appreciate that. Comments section below, put your comments, suggestions, questions, whatever you want to communicate to me in the video description below. By the way, this video was prompted by a comment left by one of my viewers who was asking about power supplies or more reliable power supplies for Raspberry Pis. And as you saw, this is pretty heavy duty, works great. Gives you a lot of flexibility, including the ability of, putting 2 or 3 of these on one power supply and powering 2 or 3 Raspberry Pis. And, I got a 90-watt power pack, and it could probably power, obviously about, well, this divided by 2, 4, maybe 5 of those, probably 6 Raspberry Pis using these. So, yeah, really nice alternative. And again, as I said throughout the video, very flexible on power input. So, off-grid scenarios where you want your Raspberry Pi to run, like a boat, a car, an RV, a camp, wherever, solar panels, great solution for that as well. Okay, so again, thank you so much for watching. Thank you for supporting my work, and we'll see you on the next video.